You know, you know that one person who just gets a perfect score on every single practice exam?
Oh, yeah, like effortlessly.
Right. But then the second you put them in a real world scenario, they completely freeze.
Exactly. It's this classic illusion of competence. They look brilliant on paper, but the actual knowledge is, entirely brittle. They haven't actually learned the underlying concepts at all.
They've just memorized the answers to the test.
Right.
And here's what's fascinating, and really the whole point of our deep dive today.
Mm,
Artificial intelligence models do the exact same thing.
they absolutely do.
You can spend like weeks training a neural network, watch its accuracy hit 99%, and you're just sitting there feeling like an absolute genius.
Oh, I've been there.
Right. But the moment you hand it fresh data stuff it has never seen before, that accuracy instantly drops to, I don't know, 65%.
Hmm.
It completely falls apart.
Yeah, it's heartbreaking.
So today, we're doing a deep dive into this exact phenomenon. We're unpacking a massive stack of sources, from textbook theory to cutting-edge ARCS papers, to figure out why machines cheat, why being too smart is actually a massive liability.
It's essentially the ultimate paper tiger problem in machine learning.
Okay, let's unpack this. What do we actually call this paper tiger problem?
So what you're describing, that massive gap between a 99% training score and a 65% real-world score, is the textbook definition of overfitting.
Overfitting, yeah.
Yeah. The model has basically memorized the specific noise, the quirks, the random anomalies of your training data, rather than actually abstracting the underlying patterns.
When you say noise, what are we actually talking about in practice?
Think about it like trying to teach a system to identify a tree.
Okay.
A good model learns that trees generally have trunks, branches, leaves. But if every single picture of a tree in your training set just happens to have a bird sitting on a
And
branch...
the AI thinks the bird is part of the tree.
Exactly. An overfitted model might decide that a bird is a strict biological requirement of a tree. It's paying way too much attention to specific, irrelevant details.
That's wild.
Yeah, and in machine learning, we describe this as a model having high variance. It's just overly sensitive to the exact data points it was trained on.
So it's hyperfixating. And on the flip side of that, you have underfitting, right? Which is high bias.
Correct. Underfitting is when the model is just way too simple, like it can't even grasp the basic patterns.
Give me an example of that.
So if you try to teach it the difference between a cat and a dog, and it just classifies literally every animal as a cat because it's only looking at the fact that they have 4 legs,
Right.
that's underfitting. It hasn't learned the distinguishing features at all.
Okay, so underfitting is the student who just didn't study and fails everything.
Yeah.
While overfitting is the student who perfectly memorized the practice test but completely bombs the real thing.
That's a perfect way to look at it.
But why does an AI do this? I mean, what actually pushes an algorithm to just start memorizing instead of genuinely learning?
Well, it usually comes down to 3 main culprits. The first one is pretty straightforward: data scarcity.
Not having enough data.
Right. If you don't provide enough diverse examples, the model has no choice but to, fill in the blanks with false assumptions. It builds a tiny worldview.
That makes total sense. Like, if the only dog I've ever seen in my entire life is a golden retriever wearing a red collar, I'm just going to assume red collar is a genetic trait of all dogs.
Precisely. You've drawn a massive global conclusion from a tiny local anomaly.
Right. Okay, what's the second culprit?
The second cause is model capacity. We measure this using something called the hypothesis space.
The hypothesis space. That sounds very sci-fi.
It really does, but it's just, you can think of it as the menu of possible mathematical functions the model is allowed to explore to fit the data.
Okay, a menu of functions. What does that look like?
Imagine plotting some data points on a graph, say housing prices over time.
Okay, tracking the housing market.
You're right. If you try to fit those points using a simple first-degree polynomial...
Which is just a straight line, right?
Exactly, just a straight line, you are going to miss all the natural curves and fluctuations of the market.
Because the market isn't a straight line.
Right, so that is a very small hypothesis space. The model isn't complex enough, which leads to underfitting.
Okay, a straight line can't capture a complex trend. But wait, if I want to capture all those nuances, wouldn't I want to give the model, like, the biggest hypothesis space possible?
You would think so.
Like a super complex fifth-degree polynomial that can just curve and bend however it wants?
You definitely think so, but that's actually a really dangerous trap.
Really? Why?
Because if you give the model too much flexibility, that line will weave wildly up and down, right? It'll contort itself to hit every single training data point perfectly.
But isn't that the goal? Hitting the points?
Well, no, because data is never perfect. It contains measurement errors, typos,
Oh, I
outliers.
see.
By hitting every point perfectly, your incredibly complex line has just captured all the errors instead of the true underlying smooth curve of the market.
So the moment a new unseen data point comes in, that chaotic line is going to completely miss it.
Exactly. Being quote-unquote too smart or too complex actually makes the model incredibly rigid. It's so perfectly molded to the past that it can't adapt to the future.
That is fascinating. Okay, what's the third cause?
That ties directly into the third cause, which is just training for too long.
Oh, right. If you do the exact same 10 practice questions 1,000 times, you aren't learning math anymore. You're literally just memorizing the sequence of the answers, A, B, C, D.
Exactly.
So how do we actually fix this? Because my first instinct is just get more data. If the model sees 10 million examples instead of 10, it's mathematically impossible for it to memorize all the quirks, right?
Getting massive amounts of high-quality data is absolutely the gold standard. It forces the model to generalize.
So just do that.
Well, in reality, you can't always just magically summon 10,000 more labeled MRI scans, or thousands of hours of translated audio. Gathering clean data is incredibly expensive and time-consuming.
Okay, fair point. So if I'm stuck with my tiny data set, what's my move?
We use a technique called data augmentation.
Data augmentation.
Right. You take the data you already have and you alter it mathematically to create new synthetic examples.
How so?
Well, say you have one picture of a cat. You don't just feed it to the model once. You rotate it 90 degrees. You crop out the background. You flip it horizontally. You intentionally add static or digital noise.
Wait, hold on. If I flip a picture of a cat upside down, I, as a human, still know it's the exact same cat.
Right.
Does that really trick a massive neural network into thinking it's looking at completely new data?
It absolutely does. And here's why. A computer doesn't see a cat. It sees a grid of numbers representing pixel values.
Oh, right. It's just math to them.
Exactly. So when you flip an image horizontally, that entire matrix of numbers shifts. To the algorithm, it looks like an entirely new mathematical input.
Oh, wow.
By forcing the model to classify all these distorted, noisy flip matrices as cat, you strip away its ability to rely on superficial detail.
It can't assume a cat is strictly a front-facing shape and good lighting.
Right. It actually has to learn the fundamental geometric structure.
That is brilliant. We're essentially artificially inflating our data set by making our existing data work harder.
Yep.
Well, let's say we've done that right, and the model is still contorting itself into that chaotic, hyper-complex fifth-degree polynomial we talked about earlier. How do we pull it back?
That is where we bring in regularization.
Regularization, okay.
If data augmentation changes the input, regularization changes the internal math of the network itself. What's fascinating here is it's basically a mathematical way to keep the model grounded by penalizing overly large weights.
Okay, penalizing large weights. Can we put that in, like, human terms?
Yeah. Sure. Think about how a neural network makes decisions. It assigns a weight, or a level of importance, to every single feature it looks at.
Right.
If a model is predicting housing prices, it might assign a weight to the square footage, a weight to the neighborhood, and a weight to the color of the front door.
Okay.
If the model starts overfitting, it might give a massively outsized weight to the color of the door just because, by pure chance, all the expensive houses in the training set happen to have red doors.
Oh, so it just assumes red door equals $1 million mansion.
Exactly. So regularization steps in and mathematically says no single feature gets to dominate the decision. It forces the weights to stay small and balanced.
It's like telling a kid, hey, don't be so extreme. The world isn't black and white, so don't hinge your entire worldview on one single thing.
That's exactly it. And mathematically, we usually do this in two ways, L1 and L2 regularization.
L1 and L2.
Yeah. Both of them add a penalty to the network's loss function, which is basically the ultimate scorecard the model is trying to minimize. L1, which is also called lasso regularization, adds the absolute value of the weights to that penalty score.
What does that actually do, practically?
Because of how the absolute value function calculates gradients, it does something highly specific. It pushes the weights of less important features all the way down to exactly 0.
Wait, if the weight is exactly 0, the model is completely ignoring that feature.
Yes. It acts as an aggressive, built-in feature selector. If you feed the model 1,000 variables, L1 will figure out which ones are useless and literally delete them from the equation.
That's brutal, but I love it. So that's L1. What about L2?
L2, or ridge regularization, adds the squared value of the weights to the penalty score.
Okay, let me think about this. If I square a tiny number, like 0.1, it becomes 0.01, so it gets even smaller.
Right.
But it never actually hits 0. So L2 doesn't throw anything away.
You've nailed the exact difference. Because L2 uses squares, it massively penalizes huge weights, because squaring a big number makes a huge penalty. But as the weights get smaller, the penalty sort of papers off. So the weights shrink, but they rarely hit absolute 0. L2 keeps all the features in the mix, but just tones them down. This is incredibly useful when you have what we call multicollinear features.
Let's define that. Multicollinear features.
It basically just means features that contain the exact same information.
Like what?
Think of house square footage and number of bedrooms.
Yeah.
They're highly correlated, right? They move together.
Right. Bigger house, more bedrooms.
Exactly. So L1 might randomly kill one and keep the other, but L2 will just shrink them both equally, which promotes a much more stable model overall.
So tell me if this makes sense. L1 is like an aggressive minimalist going through their closet and literally throwing out every single piece of clothing they haven't worn in a year.
Ah, yes.
But L2 is like keeping everything in your closet. You just make sure you don't wear your neon pink suit every single day. You just tone it down.
That is a very accurate way to visualize it. L1 cleans out the closet, L2 tones down the outfits. And actually, if you have a massive data set and you want the benefits of both, you can use something called elastic net.
Elastic net.
Yeah, it's just an equation that blends the L1 and L2 penalties together.
Okay, so we've augmented the data. We've mathematically restricted the weights using regularization. But what about the actual structure of the network itself? I want to talk about dropout.
Oh, dropout is fascinating.
Because the concept here is wild. Let's use the company analogy from the sources. If a company relies entirely on one superstar genius employee, everything is amazing right up until that person gets sick.
Right.
Then the entire department just falls apart because no one else knows how to do the work.
And neural networks do the exact same thing. During training, certain neurons can become those superstars.
Really? They just take over?
Yeah, the network realizes these specific neurons are really good at minimizing the error, so it just starts routing everything through them. We call this co-adaptation.
Co-adaptation.
Yeah, the surrounding neurons become lazy, and the network becomes incredibly fragile. So if those superstar neurons encounter unfamiliar data in the real world and make a mistake, the whole prediction just collapses.
So to fix this, dropout literally just fires random employees for the day.
Temporarily, yes. During every single training pass, dropout randomly turns off a percentage of neurons in the layer. It zeroes out their outputs entirely.
But doesn't that completely cripple the network?
I mean, it slows down training, absolutely.
Right. Yeah.
Mathematically, it follows a Bernoulli distribution.
What do you mean?
Think of it like flipping a weighted coin for every single neuron. If the probability to retain is set to 0.5, every neuron has a 50% chance of just disappearing for that specific forward pass.
Wow.
Because no single neuron can be guaranteed to exist on any given run, the network is physically incapable of relying on superstars. It's forced to distribute the learning. The lazy neurons basically have to step up and learn the patterns.
That is so counterintuitive. You are intentionally sabotaging the network during training to force it to build multiple overlapping pathways.
Exactly. And then when you switch to the testing phase, the real world, you stop dropping neurons. You turn them all back on. But because there are more active neurons than there were during training, you have to scale their output weights down mathematically so the total signal doesn't explode.
Got it.
Effectively, dropout trains millions of different smaller subnetworks, and then in the test phase, it acts like an ensemble, averaging all their predictions together into one incredibly robust answer.
Love that. You make the training chaotic so the final result is bulletproof. But okay, dropout takes time. And earlier you said one of the main causes of overfitting is just training for too long.
Right.
If I have a robust network, but I just leave it running for 3 days, it's still going to memorize the noise eventually.
Right.
How do we know when to pull the plug?
We use a technique called early stopping. It relies entirely on monitoring the learning curve.
It's like carving a statue out of marble.
Right.
At first, you're chiseling away the rough edges, the shape is getting better. But if you don't stop when the statue is done, you start chipping into the core structure and completely ruin it.
That's exactly it.
You have to know the exact moment to drop the chisel. How does an AI know when to drop the chisel?
You plot 2 lines on a graph over time, your training accuracy and your validation accuracy.
Yeah.
Your validation data is a small set of data the model is tested on during training, but never allowed to learn from.
So it's like a pop quiz.
Yes. In the beginning, both lines go up. The model is learning real patterns, so it does better on both the training set and the validation set.
Right, the statue's taking shape.
But eventually you hit a critical point. The training accuracy will keep climbing toward 99%, but the validation accuracy will suddenly plateau, and then it will actually start dropping.
Because it stopped looking at the big picture and started memorizing the specific bumps and scratches on the training data.
Exactly. That point of divergence, the exact moment a gap opens up between the training line going up and the validation line going down, is the precise second overfitting begins. Early stopping is just an algorithm that watches those two lines and automatically halts the training process right at that peak, before the memorization phase can take over.
Okay, so we have all these amazing tools: regularization, dropout, early stopping. But here is something in the sources that really caught my eye.
Oh, yeah.
What happens when you combine two of the most powerful optimization tools in machine learning, specifically dropout and batch normalization? If both are great, putting them together should make a super tool, right?
You would certainly think so. I mean, batch normalization, or BN, is a fantastic technique.
What does it do?
Well, as data passes through the layers of a network, the distribution of those numbers can shift wildly. BN standardizes the inputs of each layer, so they have a mean of 0 and a variance of 1. It drastically speeds up training.
Okay, sounds great.
But when you combine batch normalization with dropout, the model's real-world performance often completely tanks. They actively fight each other.
Why? They're both designed to help the network generalize. How do they clash?
The problem lies in a hidden mechanism called variance shift.
Variance shift.
Yeah, it comes down to the fact that dropout fundamentally alters the state of the network between training and testing.
Right, because neurons are turning on and off.
Exactly. Remember, during training, dropout is randomly zeroing out neurons. This creates a very specific, chaotic level of numerical variance inside the network. Batch normalization is watching this happen during training, and it meticulously calculates a moving average of this variance so it knows how to normalize the data later.
Okay, so batch normalization is basically taking detailed notes based on a chaotic environment.
Exactly. But then you switch the model to test mode. Dropout stops dropping neurons, it leaves them all on and just scales the weights.
Oh.
Suddenly, the network is stable. The real numerical variance flowing to the layers is completely different from the chaotic moving average that batch normalization recorded during training.
Oh my God. So batch norm steps in and applies a mathematical correction based on a chaotic environment that literally no longer exists.
Yes. Because the network isn't expecting all those neurons to be firing at once without being dropped, batch normalization applies the wrong scaling factor.
Wow.
The signals get blown completely out of proportion as they move from layer to layer, turning the final prediction into pure garbage.
That is wild. The variance shift completely destabilizes the math. So what's the fix? Do we just have to abandon one of them?
Not necessarily. There are architectural solutions. The simplest fix is to just change the order of operations. Apply dropout only after all the batch normalization layers have done their job.
Oh, I see.
Yeah, if BN happens first, before the neurons are dropped, it calculates its statistics on stable data, so there's no variance shift to worry about.
Smart.
Another solution involves modifying dropout itself into something called OOT, which uses a continuous uniform distribution instead of a Bernoulli coin flip, making it mathematically much less sensitive to variance shifts.
It's just amazing how deep the math goes to fix these invisible clashes.
It really is.
But speaking of deep math, let's talk about label smoothing. Because normally, if I show a neural network a picture of a dog, I tell it, this is 100% a dog, it is 0% a cat, 0% a bird.
Right. Absolute certainty. We call that a one-hot vector, just zeros, and a single one.
But label smoothing takes that one-hot vector and says, no, tell the AI it's only 90% a dog and distribute the remaining 10% across all the other categories.
Exactly. It deliberately introduces doubt.
Right. And my immediate reaction to this was, why on earth would we intentionally teach a machine to be unsure of itself? I want my self-driving car to be 100% sure it's looking at a stop sign, not like 90% sure.
I know, it feels so counterintuitive, but absolute certainty is actually the enemy of generalization.
How so?
Let's look at the math. A neural network adjusts its weights to minimize the loss function. If you demand 100% confidence, the only way the math can reach a perfect zero error is by pushing its internal weights toward infinity. The model becomes hyper-rigid. But more importantly, we have to acknowledge that real-world training data is never perfectly labeled. Humans make mistakes.
True. Someone out there definitely accidentally tagged a picture of a blueberry muffin as a chihuahua.
Exactly. We call that label noise. In mathematical terms, we generally categorize this into three types from the research.
Okay, break it down.
There's alpha-type noise, where only the training data is corrupted but the testing set is clean. There's beta-type noise, where both sets have the exact same level of corruption.
I'm the third.
Gamma-type noise, which represents inherent, unavoidable ambiguity. We use a Bayesian approach here, which just means dealing with probabilities of uncertainty, like trying to classify whether a highly sarcastic sentence is positive or negative. The ground truth itself is debatable.
Oh, sarcasm breaks us all.
Yeah.
So how does label smoothing protect the model from that noise?
If a model is forced to use a one-hot vector 100% confidence, and it encounters that mislabeled muffin, it tries to force its math to achieve absolute certainty that the muffin is a dog.
Right.
The loss function requires taking the logarithm of the difference between the prediction and the label. If the label demands perfect certainty, it's essentially trying to take the logarithm of 0, which mathematically diverges toward negative infinity.
So the math just breaks.
The model literally destroys its own weights trying to accommodate an error.
Wow. So one bad label can mathematically crash the surrounding learned patterns because the math spirals out of control.
Exactly. But by smoothing the labels, telling the model, hey, just aim for 90% certainty, you cap the math, the loss function never approaches infinity. The model doesn't overcommit to errors in the training data. It builds in a margin of error.
We are quite literally teaching the AI humility. We're telling it, you don't know everything, and the data isn't perfect, so leave some room for doubt.
That's a profound way to look at it. And if you step back, every single technique we've discussed today, data augmentation, regularization, dropout, early stopping, label smoothing, they are all mechanisms designed to manage the ultimate tug-of-war in machine learning: bias versus variance.
We want a model with low bias, so it's smart enough to understand the complexity of the data, but low variance, so it doesn't overreact to the random noise.
If we connect this to the bigger picture, winning that tug-of-war is incredibly difficult for one single model.
Which brings us to our final strategy: ensemble methods. What if, instead of trying to build one perfect, godlike algorithm, we just build a team of okay algorithms?
Yes, ensembles are incredibly powerful. You stop trying to tune a single model and instead aggregate multiple models. Take a random forest, for example.
Okay.
This is an approach called bagging. In bagging, you intentionally build many deep, highly complex decision trees.
Wait, but didn't we say earlier that deep, complex models have high variance and overfit?
We did. Individually, each of those deep trees is massively overfitted to its specific random subset of data. They are highly flawed on their own.
So why use them?
Because you have a whole forest of them, and you average their predictions together. The individual overfittings, the random errors, they mathematically cancel each other out. You retain the high capability, the low bias, but the averaging drastically lowers the variance.
So it's the wisdom of the crowds. A bunch of erratic experts averaging out to one genius answer.
Exactly.
But what about AdaBoost? I know that's a boosting method, not bagging. How is that different?
AdaBoost takes the exact opposite approach. Instead of building deep, high-variance trees, it builds incredibly shallow, simple models, often just single-stump decision trees that look at one variable.
Oh, that's terrible.
They severely underfit the data. They have high bias.
Wait, you're telling me chaining together a bunch of terrible models that are barely guessing better than a coin flip makes a great model? How does that even work?
Because of how they are chained sequentially. The first simple tree makes its prediction. It gets some right and some wrong. The AdaBoost algorithm then looks at the errors and essentially highlights them, increasing the mathematical weight of the misclassified data. The next simple tree is then forced to focus specifically on those harder highlighted problems. It corrects the errors of the first tree.
Oh, it's sequential error correction.
Exactly. By combining hundreds of these weak learners, where each one compensates for the blind spots of the last, you gradually drive down the bias without ever exploding the variance.
That is absolutely brilliant. You know, looking at all of this is a really incredible parallel here.
How so?
In the machine learning world, we spend millions of dollars and massive amounts of computational power intentionally adding noise to our data. We aggressively restrict our parameters. We artificially turn off our best performing neurons just to see what happens.
We do.
We mathematically force our algorithms to be just a little bit less certain about their answers. We literally engineer uncertainty into the system.
We have to, because the real world is infinitely unpredictable. And rigid certainty is incredibly brittle. A system that is perfectly, flawlessly molded to its past will completely shatter the moment it meets an unpredictable future.
It really makes you think. If the smartest, most advanced AI systems in the world require engineered uncertainty, forced forgetting, and a built-in margin of doubt just to truly understand the world,
Right.
maybe we humans shouldn't be so obsessed with having 100% certainty about our own rigid beliefs.
That's a great point.
Something for you to chew on next time you are absolutely sure you have all the answers. Thank you so much for joining us for this deep dive. Whether you're optimizing a neural network today or just trying to navigate a messy world, remember to leave a little room for doubt. We'll see you on the next deep dive.